Hi, everyone. Dr. Smith here. Today, we're going to be talking about Chapter 3, Reliability and its importance, getting right every time. So it's one of the most important ideas in tests and measurements. It's reliability. At its core, reliability asks a very simple question. Can we trust the scores we get? If we gave someone the same assessment multiple times and nothing important changed, would the score stay relatively stable? Because if a score bounces around randomly, then we have a problem. So, as counselors, researchers, and clinicians, we make decisions based on scores. If those scores aren't consistent, our decisions become much harder to trust. So, diving in, let's start with this definition of reliability. So, reliability refers to how much randomness there is in a bunch of scores. So, reliability is really just about consistency and randomness. The more randomness we have, the less reliable a measure becomes. I want you to think about this really quick. Think about stepping on a bathroom scale 5 times in 30 seconds. If it says 150, 151, 150, 149, 150, right? That's pretty consistent. Now imagine you do the same thing and it says 150, 174, 132, 161, 179. Something's wrong, right? And the problem isn't you. The problem is the measurement tool. Maybe it needs new batteries. Who knows? But good assessments are going to work the same way. We want low randomness, high consistency. So you may be asking, well then how do we actually measure reliability? Well, to quantify reliability, we just need numbers. Two common approaches to this are test-retest reliability and inter-rater reliability. So test-retest asks, do scores stay stable over time? Inter-rater reliability says, do observers agree with each other? Okay, and so these become ways to put a number on the consistency. So this is where students often get confused. So let's slow down a little bit. There is an observed score. That's easy. It's what someone actually earns. So if I make a test, a quiz, and it's out of 100 points and a student gets an 82, that's their observed score. Now, true score is different. It's theoretical, and we'll come back to that. So if the person's actual level of ability or performance, if we could measure them perfectly, that would be the true score, right? So for analogy here, think about archery, all right? So the bullseye then represents the true ability. If you pull back the bow and you let it go and it hits that bullseye, that would be the true ability. Now, the arrows landing around that bullseye, those are then the observed scores. So sometimes you're close and sometimes you're farther away. That distance, that is error. That's the error score. So a couple things to remember. No test is perfect. Humans aren't perfectly consistent. Testing conditions aren't perfect. Randomness exists. So let's think about GPS navigation. Your GPS usually gets you very close, but sometimes you're 10 feet off, okay? So usually close, but rarely perfect. Testing instruments work similarly. So our goal in this is not perfection. Our goal will always be to minimize the error. So let's talk about the error. The error is the difference between one's observed score and one's theoretical true score. So where does this error come from? Well, sometimes it's the person, right? Maybe the person taking the assessment is anxious or tired or distracted or they didn't study. Sometimes the error comes from administration. Maybe the room is loud or warm and it makes them sleepy, or maybe the instructions are confusing, or the testing procedures differ. All of these factors create a noise that hides their true performance. So reliability is really just about precision. Again, back to that dartboard. Closer that we get consistently to hitting that target, the more precise we are. The more precise we are, the more reliable the instrument becomes. So now we move into classical test theory. This is one of the foundational ideas in psychometrics, and I touched on it last week with you. The formula is simple. So that observed score, right, equals the true score plus any error. So we're accounting for the error and that true score, and so that's what the observed score is. So say that student that got an 82, okay? Well, there's some error that probably occurred while they were taking the exam, right? And then the true score is in there. This is all the backbone, and we're going to get into this a little bit more. But if we look at the differences, right, we expand on this error in some different sources, we see trait error and method error. So we're going to include those in. But the basic idea stays the same. So don't let me lose you, all right? Trait error is going to come from the person. So maybe they're tired, anxious, distracted. And then method error is going to come from the administration. Maybe it's a loud room. There's poor instructions, confusing testing conditions. Okay, here's an analogy. I love analogies. Think about baking cookies. The trait error when baking cookies, the baker forgot sugar. The method error, the oven temperature was wrong. Two different problems, same result, final product changes, okay? So reliability improves when that error decreases, okay? So less error means the observed scores get closer and closer to the true scores. And ultimately, that's the whole goal here, right? We want to reduce the noise and increase precision. So classical test theory isn't the only framework. We talked last week about item response theory, or IRT, and it approaches testing differently. It's looking at the individual items. So it looks at both the person taking the test and the characteristics of the questions themselves. Some other books call this latent trait theory, okay? But all that matters here is that traits matter and items matter, and both of those will influence the performance. Okay, two different frameworks, but that's where they stand on this. So let's talk about putting a number on this reliability, because we often measure reliability with a number, and that's called a correlation. Right? We often use correlations to measure how reliable something is. So when you're working on your project or your portfolio, I'm going to be asking you to find that correlation, right? Find those values. So a correlation tells us how strongly two things move together. So if you look at the image here, we see scatter plots, and we look at a positive correlation. There's a bunch of dots, and they're moving in the same direction up and to the right. And because it's going to the right, it just means positive, right? If you think of a number line, we have our positive numbers going to the right, and this is going up to the right. And then negative correlations is moving to the left. Again, that number line, right? We have it going as your numbers move from right to left, the numbers become lower. So it's a negative correlation, but they're all clumped together going in the same direction. So there is a correlation. And the third one, no correlation. Dots are just randomly all over the place. So a higher correlation suggests greater consistency. And then reliability coefficients, these numbers that we're looking for, and correlation coefficients, fairly similar, okay? The reliability correlation coefficient, or the reliability coefficient, is going to range from 0 to 1. Closer to 1 generally means stronger reliability. The correlation coefficient is going to go from -1 to +1. Okay? We're really usually looking at positive, but it's going to indicate the direction of the correlation. And so positive correlation would be over 0 to 1, and negative correlation would be 0 to -1. And it just means that the items are trending in a negative direction or a positive direction, and that's all. So let's look at this, right? Let's look at some data. Yay, data. Okay. So we see scores of 15 adults on a 10-item achievement test that were taken at 2 different times. So you see column 1 is ID, column 4 is ID. And so that will give you all of the 15 adults that took it, September and October test. That's what you're looking at here. So if you notice these September and October scores, you see person 1 has 78, 79. Person number 9 had a 69, 72. fairly consistent across them, though. So none of these people are identical, but they're all pretty similar. So that similarity produces a strong correlation. And as a matter of fact, when we run the numbers on this for their correlation coefficient, it came out at a 0.90, which means that they're pretty strongly correlated. So when we see strong relationships like this over time, we gain confidence that that measure is reliable. So speaking of over time, let's look at retest reliability. So that's talking about whether a test is reliable over time. Can we give the test and then retest and have similar scores? Because if nothing meaningful changed, the scores should then remain relatively similar. So go back to that scale analogy. Think about weighing yourself 2 mornings in a row. The numbers might move slightly. They should not completely change, right? That helps increase our confidence that we're getting a reliable measure. One challenge of retest reliability is practice effects. So people remember things. Exposure to something already can change the performance, and time matters too, right? Especially in development. So if we're testing a child that is 4 and then when they come back, they're 6, right? Children can change rapidly. So waiting months in between tests can create some real differences instead of measurement differences. And so we just have to be aware of that. Now, inter-rater reliability, onto that. So remember, that asks, do observers agree, right? So we asked Fatima and Jordan to rate this, and do their scores, are they close, right? So imagine 2 supervisors watching the same counseling role play. One says, wow, excellent empathy. And the other says, boo, poor empathy. That's a problem, right? They should both observe the same thing if there's a high inter-rater reliability. So the agreement between them improves the confidence. Oh, well, if they both say that, then wow, I must be doing great with empathy. But if one says excellent, the other says poor, well, now I'm not so confident. I don't know where I stand with this, right? And so more similar ratings and higher inter-rater reliability. Okay, we see, so to ensure that what we are recording is reliable, we must find out the level of agreement between the 2 different observers. The more similar the ratings are, the higher the level of inter-rater agreement and inter-rater reliability. Okay, so we see the formula here is inter-rater reliability is equal to the number of agreements over the number of possible agreements. So there's 10 things and we agreed on 8 out of 10. Well, our inter-rater reliability, we're at 80%. We're pretty good, okay? So in the case of inter-rater reliability, the coefficient used is an actual proportion, and this is not the case with correlations used to describe the other types of reliability that I showed you earlier. So here we go. We have 2 raters. They've noted every 10 seconds if a banker is demonstrating one of the 3 behaviors. So are they smiling? Are they leaning forward in their chair? Are they using their hands to make a point? And they've rated it. So every time they've seen that, they'll do a slash. So the slashes in the table indicate the presence, and the dashes indicate the absence of these acts. So the important variable is whether or not any one of the 3 acts occurred within a set of 10-second time frames across 2 minutes. I hope I explained that well. It's kind of difficult to see. So for a total of 12 periods, there are 7 where both raters agreed that that happened. Do you see? Like for 1, 3, 4, 5, 7, 8, and 12. Okay, there's 7 times where they both agreed that that happened. There's 3 where they agreed the banker did not. And for a total of 10 agreements. So there's 10 agreements that they agreed on and 2 disagreements, okay? So to do that, we're gonna compute to figure this out, we're gonna compute the inter-rater reliability as follows, okay? So remember, inter-rater reliability, right? They had 10 out of 12, okay? So their inter-rater reliability then is 0.833, repeating essentially, but I think on here I put 0.83. Yes. So the resulting inter-rater reliability coefficient, 0.83, which means the 2 raters agreed 83% of the time. I would say that's pretty good. Okay. We want to get closer to 100. 90, but 80 is pretty good. Okay. Also, there are parallel forms of reliability, and that examines the equivalence or similarity between two different forms of the same test. So I give a quiz and I have different questions all moved around, right? Same questions, just moved all around, right? So in order to do this, like you can use item sampling. So the sample of scores are taken using the different sets of items. So this one question is maybe the 5th question in the test here and the 7th question here, and we compare how they did on those. Right? And so, where was I? Use of different forms of standardized tests. So large commercial test development companies, which you may be familiar, that make these standardized tests like what we have to take, the NCE, the NCMHCE, the ACT, the SAT, right? They use these different forms all the time. So the ACT taken by a person in New York is not the same one that a person may take in California. So it's clear that the ACT company has established these parallel forms of reliability for their different test forms. Okay. Another way to quantify reliability is this internal consistency, and it asks whether items belong together. So are all of these items measuring the same thing? So think about a band. If every musician is playing the same song, things are going to sound coherent. If one person is playing jazz while everyone else is playing classical, or one person is doing rock music while everyone's playing classical, something's going to feel off. So good assessment items should work together. So we want to look at their internal consistency reliability. And then we have split half. Okay. And so with this, it's a classic way to measure their internal consistency. And so it involves taking the test and splitting into two halves, and the scores on the two halves are compared then to determine the relationship. Okay. Now, more reliability and less room for change is talking about the amount of increase for corrected split half reliability coefficients decreases as the original split half reliability coefficient increases. Essentially, this is just saying that the more reliable the original estimate of what we're going to measure, right, the more reliable it is, the less room for improvement when we correct it. So, long story short, shorter tests are less reliable than longer ones because there's less to split to compare. There's less data. There's more chances to, or the more chances to respond decreases the amount of randomness in the total score. So more observations increase precision. Long story short, shorter tests are always going to be less reliable than longer ones. Now we know that short tests, clients like short tests. They don't want to answer a bunch of questions. But I want you to remember when you're selecting your assessments for your clients that just because it has 4 questions, like the cage, it does not mean that it is more reliable because it's not. In this case, the audit would be more reliable. More questions, more opportunity to compare. Okay. All right. Don't let me lose you here. Okay. Cronbach's alpha, or that should be the alpha symbol there. All it's doing is measuring the internal consistency of this assessment. So higher alpha values, if we do this math and higher alpha values, and we have higher alpha values, that's suggesting that these items that we have are working together. Okay. So rule of thumb, around 0.70 is often acceptable. I'll show this in the next one. Around 0.80 is stronger. So extremely high values, however, may suggest redundancy, but let's not worry about that just yet. So we're looking at all these coefficients. We're talking about all these coefficients, interpreting all the coefficients. So a reliability coefficient is essentially a trust score for our assessment. We want to know, can we trust this assessment? And the closer we get to 1.0, the closer we are and the more confidence we have that the assessment is producing stable, consistent information. So think of it like this. Okay, think of it like weather forecasting. If a weather app predicts tomorrow accurately 95% of the time, we're going to trust that app more than one that's only accurate 50% of the time. I know me, I have a weather app that I go to because it's fairly consistent. Okay. Off to the right side here, you just see a visual of 0.90, excellent consistency, 0.80, strong, etc., etc. All right, so we do all of this. We try to make sure that the assessment is reliable. What if you can't establish reliability? What do I do now? What points do I need to consider to achieve this reliability, to minimize the test score, all the variance, right? What are some points? Well, you need to make sure that the instructions are standardized across all settings when the test is administered. So I'm going to tell you to read the manual, and I'm going to give the client the instructions exactly as the manual says. We're going to make sure that everything is administered in a standardized way. Increase the number of items in the assessment. Find one that has an increased number of items or observations, because the larger the sample that we have, the more likely the sample is going to be representative and reliable. And that's especially true for like achievement tests like SATs and ACTs, etc. And then if we're making an assessment, right, and we're measuring the inter rate or the items, measuring the items, and we see, oh, for me, if I look at a test, I always go and I look and see, did all my students get this question wrong? That must have been an unclear item. I'm going to remove that, right? So if you're building an assessment, the book is talking to us about how to build the assessment, we would delete unclear items because people will respond in one way on one occasion and another way in a different occasion, regardless of their knowledge, ability level, or individual traits. So we need to get rid of those. All right. And last but not least, if you remember one thing from this video, remember this: reliability comes first, right? When creating an instrument, when determining what assessment to use, right? We're always looking for reliability, even in our friendships, even in our relationships with others, right? We want to make sure we're choosing people that are reliable, that are going to do what they say they're going to do, right? They're reliable, they're going to be consistent. Let's say that. We're going to say they're going to be consistent. So reliability comes first. So if scores are random, then the interpretation becomes difficult, right? It's just random. It's hard to determine what's going on with that. Good measurement reduces the randomness, improves the consistency, and it gives us more confidence in the decisions we make as counselors and as researchers. All right. This is it. Remember, you made it all the way here. Remember that I will be on Zoom this week if you need additional support, right? You can email me. You can hop on the Zoom at 6. I'll be on my Zoom page at 6 if you have questions about any of this. Okay. I think the book actually did a phenomenal job of explaining these concepts. But if you have questions, I'll be on there. And I'll be on there until no one else is on there. So if it's 6:30 and no one's on there, I'm not staying on there. But you can always get me. Email me, set up a time to meet with me. I'm here to support you. You guys have a wonderful week. I missed you. Sad not seeing you tonight, but I'll see you next week. Take care.